Yeah, so we are recording. That's very. Yeah, so this is maybe a couple of lectures. I hope it just stops at a couple of lectures. Things we need to know before starting reading quantum field theory and also random matrix theory and stuff. Yeah, so there's a little bit of physics background. I mean, classical quantum physics, but very, very brief. I mean, just things that we absolutely have to know before start thinking about QFT. Okay, so yeah, so this is in calendar. Okay, yeah. So the first thing is just a little bit about classical mechanics we have to know. Okay, so most of physical theories, when you start a mathematical treatment of physical theories, you need to specify two things. One is kinematics. And the second is dynamics. So in kinematics, we don't discuss motion. We just discuss the settings that is necessary to talk about motion. So we just specify our settings. And with dynamics, then comes equations of motions and things like that. So with kinematics, the setting and also the kind of mathematical objects, is it particles, fields, or this sort of things we discuss. So the kinematics of basically classical mechanics is consists of a point, or points in n-dimensional space Rn. And what we are interested in is the motion of particles in Rn. Right? So basically curves, I can write some math even. So my notation is going to be rather ambiguous, but that's good. So I also think of Q as a map from some interval inside R to Rn. So this is the path of a particle moves in Rn. Question?
So Q is both a point and a path?
Yeah, I mean, sometimes I denote it as a point in Rn, and sometimes also I think of Q as Q of T. Okay. Most of the time, I hope there's no confusion. Okay. Yeah, that's okay. So yeah, and we want to know what are the equations of motion for this path. By the way, you may say the real space is three-dimensional or two-dimensional, one-dimensional. Why we are in n dimensions? And the point is that, first of all, it's good to have something in n dimensions. In general, maybe space is n dimensional. Someone eventually will emerge sometime that, and then we want to have classical mechanics in higher dimensional spaces. But even more important than that, perhaps, we need to think of Q as a collective kind of coordinates for not maybe one particle, but set of particles. So if you have n particles, each of them are moving three-dimensional space. So k particle, each of them moving in three-dimensional space. So the total coordinate for that would be 3k. So n would be, in that case, 3k. But we can still think of it as one. So k particles in R3 is like one particle in R to the power 3k. That's kind of bookkeeping we can have in mind, but just we can think of one particle moving in Rn. And okay, so this is called configuration space, by the way. I mean, this is typically called configuration space. All right, so now So to discuss, okay, so now to discuss dynamics. So in Newtonian mechanics, that's what Newton taught us. We are given a function f, which is this is called a force field. So you can think of force field f as a function from Rn plus R to Rn at first. So this is like, we denote it by f of q and t. So this is a vector field that's defined on Rn, and is a time-dependent vector field in general. Time-dependent vector field. Of course, you don't have to have time-dependent. You can have time-independent vector fields. Many times your vector fields, the force field is time-independent. You can even be a little more general than that, actually quite more general than that, and consider actually f not as a function of Rn, so as a function of Rn cross Rn cross R to Rn. So this we denoted, I'll tell you what it means, f of q dot. The second variable I'm going to denote by q dot, just for now, just a notation. And it's t. So the idea of this kind of force fields that you may face at one point in your life is that there are forces in nature that depend on velocity, not just position and time. And these are the more complicated forces. The forces that, can you tell me an example of a force that would depend on velocity also? Yes. The Lorentz force of relativity is such a force, but something more mundane maybe in everyday life. Well, Lorentz is also everyday life, but something much more mundane maybe.
It's a dumb question, but if it depends on q dot, then can't you say it all depends on q?
No, they are independent of each other. This, yeah, so this is again notation. Q dot, think of it as a new point in this coordinate. Yeah,
it's not actually, yes, I'm okay.
Yeah. This is the, so I'm using deliberately, I'm using physics notations so that you, when you learn text, you can.
Right.
Yeah, but that's a good question. Yeah. Okay, so a force that's is a force that we, every moment in life we are dealing with it actually.
Yeah.
No.
No, that's not.
It's a force of friction, for example. Friction depends on velocity. And the more velocity is, the force of friction is higher. So when you rub your shoe on the floor, if you move it faster, there's more force resisting that motion compared to when you move it slowly. And also when I drop a chalk, the faster it moves, it faces more force in the opposite direction, resisting force, which is force of friction between gas molecules, air molecules, and the chalk. But yeah.
That's what I think.
Yeah, these are, yeah, Jeremy. If you have questions, yeah, feel free. Of course, yeah, it's very important to ask questions, otherwise. Okay, but honestly, we can just think of F just as Q. So this would be a force. This is the simplest kind of force that just depends on position. Usually, that's kind of, for example, force of gravity or electrostatic force between two particles just depends on the position of the particles and nothing else. Just electrostatic, not electrodynamics, as it was said. All right, anyhow, so we have this. So then we have Newton's equation. That's the thing. So basically, it's F equal to ma. So this F, of course, is our force, and A is acceleration. So this is acceleration, and by definition, this is the second derivative of this particle that's moving in space. Acceleration is second derivative. So, I mean, this Newton's equation, then we can just mathematically write it as m q double dot equal to f of q dot and t. This is the kind of most general case. Now, you have to realize, of course, this is not one equation, this is a system of equations, right? So this is really mqi double dot equal to fi, because it has to hold for each coordinate of the things, right? Fi of q dot and t, right? I equal to 1, 2, and so this is the famous equations of Newton. M is mass of the particle. So, yeah, so the force is related to acceleration. And the ratio is M. Okay, so what does this equation tells us? This equation tells us that if for any time t0, and for any initial vectors like q0 and q0 dot initial vectors. So these are like initial position and velocity. There exists a unique path q from interval t0 minus epsilon to t0 plus epsilon to Rn that satisfies this equation. Right? So, of course, this needs a proof, and the proof is one of the fundamental theorems of ordinary differential equations by ordinary differential equations theory. So if I know the initial position and initial velocity at some moment of time, then I know the particle's path in the past, immediate past, the vicinity before t0 and vicinity after t0. We may not be able to say that this can be continued for all times, before or after. Things may happen. For example, a collision may occur in finite time and things like that. But at least in some interval around t0, the problem has a unique solution. And this is the determinism, right? This is the principle of determinism, which is so ingrained in classical mechanics. Let me write it here. So this is the so-called Newton Douglas principle of determinism. So Laplace famously said that give me the position, state of the universe at some moment in time and its velocities, then I can tell you what's going to happen in the universe forever. And actually what has happened before that as well. So you can also not only predict, but you can also predict backward. I don't know what's it called. So this is, yeah, question? Sure.
Maybe kind of a basic question, but this theorem from ODEs that tells you there's a unique solution. This works even for nonlinear equations, for example,
Yes.
like q dot squared.
Yes. Yeah, that's right. Yeah, that's it. Yeah, the solution is always unique, even when it's a square, like nonlinear or q squared, q dot squared. And in fact, this nonlinearity causes the solutions to blow up in finite time often. So, but if it's kind of linear, the solutions exist at all times. But nonlinearity causes solutions to blow up or go to infinity in finite time. So if particle escapes in finite time to infinity, then there are no. Yeah. So this is so let me give you an example. Simple example. I mean, I wrote it in the most general form, but usually we just have Q again. I just emphasize. I mean, you don't deal with friction, we don't deal with time dependence. It's just position. In that case, that's what perhaps maybe in physics 101 we learned we learned of thinking of Newton's equations as such, but it's definitely in Q dot. But you see, I cannot put a force field that depends on the second derivative or third derivative. This never works in Newtonian mechanics. I mean, this principle of determinism will not hold. I mean, this is apparently not a mathematical thing. This is also a fact of nature, which classically can be observed. If you know, in many situations, if you know position and velocity, you can tell that the system is moving in a very determinate path. It takes a determinate path.
So if you have higher dependence, then does the theorem always not hold if you have higher dependence?
The theorem holds, but then we don't have this just unique, just position and velocity dependence.
Okay,
you must specify more, but that's not observed in nature.
Oh, okay.
What is observed is that with velocity and initial position, initial velocity, everything is determined. And this is kind of ingrained in or verified by Newton's equations as well. Newton's equation. Okay, so the simplest example, of course, is when, or what should I do with this? What should we take for f in the simplest example? Yeah, f equal to 0. Yeah, exactly. No force. Then in that case, of course, we have this equation that mq double dot equal to 0, right? And we know how to solve these equations. Of course, the solution is going to be q of t is going to be a plus bt. So I deliberately writing it in this form to denote the vector nature of these things. So given for a and b belonging to Rn. So in other words, we are saying all solutions are of this form: a dot, a hat plus b hat. I mean b vector or whatever t belonging to R. So the set of all solutions are all lines that you can imagine they are drawn in R. Just a straight line, right? Solutions are straight lines. Of course, if you specify initial point and initial velocity, which is, so this point is going to be a hat, and this vector is going to be b hat, then there exists a unique path that passes through this point, unique curve, unique straight line passes through this point and has this velocity, and this is the solution. But it's important to note that there are infinitely many solutions, of course, and they're all of this form. So what does this say? It just says that if there are no forces around, a particle is not necessarily constant in space or in a fixed position. It's moving on a straight lines with constant velocity. That's what Newton's and Galileo predicted. So what does this mean? It means that Newton's equations are true only in inertial coordinate systems, not in general coordinate systems. So this is very important to notice. So the corollary is that Newton's equations are valid only in inertial coordinate systems. That's so Newton's equations are not true, for example, in a train that's moving with acceleration with respect to a train station. Because in that train, if you are in a bus, for example, not a train, even if you're a bus, the bus is accelerating in for a while, right? And there are no forces, but you feel force on yourself. You feel that you're pulled back. There are no forces you can attribute this to in your coordinate system, because you're not in a. The reason is that you're not in a inertial system in that case. Your system with respect to, for example, Earth is not inertial. You are in a non-inertial system. Now, this is a very important concept, of course, inertial system. And you might ask, so what is the definition of inertial system? Well, the definition of inertial system is a system in which Newton's equations hold. And only those equations, those systems are. So, of course, this raises the question, can we write equations of motion in non-inertial systems? That's absolutely, the answer is absolutely yes, you can, but it's not in this simple form. It takes a different form. It's more complicated, but it's possible to write it.
Can they simplify it to Newton's equations if you?
Yeah. Yeah. So this is a consequence. So because if F is 0, the force, the only solutions of this simple differential equation are straight lines, then it means that, and this was what Galileo observed actually, and wrote it in his book, Dialogues Concerning Two New Sciences. And he also experimentally. So the surface of Earth is like, for many things, it looks like an inertial system. If there are no frictions, there are no, if you neglect force of gravity, neglect a lot of things, something on a very flat, smooth surface, you can have small balls, and then you move it, and then you just keeps moving with the same velocity, same direction at all times. This can be reached. Of course, this is not absolutely true because friction will take over eventually, but this can be approximated to high degrees of precision. Any other questions or any questions? So, questions? Okay. Okay, so now among all forces, there is one kind of force that's very important, has very particular form, very particular nature. And that force, what can you say about that force? Or what is it called? Maybe from your physics 101 course, you have seen that force. Huh?
Harmonic oscillator.
Right. And even, yeah, absolutely. Like that follows from Hooke's law, for example. Exactly. But there is but that's a special case of something more general, which is called conservative force, right? So this is my example 2, conservative force. So now this conservative force is just is a force that depends only on position, but there exists a function u from Rn to R such that F is equal to negative gradient of u. So in other words, we know that Fi of Q is equal to negative d dqi of u of q. I equal to 1 to n. So these are called conservative forces. So this is the gradient operator. I mean, so of course, one thing we have to observe is that if you are on the line, any force is conservative on the line. Why is that? The force on the line is what? A vector is just a number in this case, right? Because if you have a basis for a space of vector field, which is just a constant vector I, and then any function is a vector field and vice versa. So we have got the vector field is just so this F, for example, goes from R or maybe some interval, it doesn't matter, from R to R. Okay, now why this function, this vector field is conservative? So what is the potential in this case? I'm saying there is a potential in this case. By the way, this U is called the potential. Yeah, so let me write it. This is called the potential. You have seen in random matrix theory so many times.
Is this the negative get integrated into that?
Yes, it's just because we can integrate, right? In this case, of course, we can just say U of Q to be negative from P0, from Q0 to Q, well, this is kind of, yeah, Q0 to Q, F of tau, d tau. Right? Because if you take derivative of this guy, you get F with negative sign. That's so we can always integrate a function on the line and get this. So this is good. I mean, this is pretty good. In one dimension, any force is conservative. So this is good. But for n bigger than or equal to 2, this is not true that any force is conservative. There are many non-conservative forces. But in fact, generically, forces are not conservative. It's very special for a force to be conservative. Why is that? Generically, I just say generically in a very loose, informal way. Generically. non-conservative.
We need some assumptions on that.
Absolutely.
Over time, so we need to be.
Yeah, we need some assumptions on this f, because we see f has two coordinates. For example, in n equal to 2, we have f1 of q, I mean, q is q1 and q2, right? And f2 of, so you have 2 times infinity functions. I mean, this is the variety of such vector fields, of the vector fields, is just so much more than this potentials, which is just one function. And in fact, necessary sufficient condition for fields to be conservative, we know what they are. We learned it in calculus, right? What is necessary? So f is conservative. What? Such a smooth and defined everywhere without holes or anything. If it's conservative, if and only if what? There is a topological condition. It's related to topology. But I mean, this equation tells you that, okay, f1, f2, right, is equal to negative du dq1, right, and du dq2, right? So it means that because mixed partial derivatives commute, it means that the derivative of f1 with respect to q2 should be equal to derivative of f2 with respect to q1. That's a necessary condition, right? This implies that the derivative of f1 with respect to q2 should be equal to the derivative of f2 with respect to q1. Right? And in topology, we are told that Poincaré lemma tells us that in R2 and Rn in general, in simply connected domains and all that, this condition, well, I mean, I don't say anything about Rn right now. I'm just on R2. We did completely discuss R. Now we are in R2, and this condition is also sufficient if there are no holes in the domain. Are you with me here? So there's a condition to be satisfied for forces to be conservative, of course. Generically, forces in dimensions 2 and higher are not conservative.
Wait, sorry, this is how did you go? What's the first implication?
I mean, from left to right?
Yeah, is you just took the derivative again?
Take the derivative again, and the mixed partial derivatives commute. Right. So that's
and then the back way is Poincaré.
So in other words, this is integrability, right? Vector fields have to be integrable in this sense. I mean, it means that they can be integrated, and this U potential is antiderivative in some sense of F in higher dimensions.
Does this mean when they say, okay, what does this mean when they say integrable?
What does this mean when they say? Yeah, so this is long story.
Is it related at all, or
it is? Oh. It is related. Yes, it is related. Yeah. It's beginning of that story.
Oh, okay.
We can discuss it in one lecture sometime. Yes. Okay, so these integrable systems in classical mechanics are much easier to understand than integral systems of quantum mechanics, which is much more elaborate. But that's okay. So this at least we know in what happens in R2, and in Rn also for n bigger than 2. yeah, we should derive some condition, which, okay, I don't want to discuss it right now, because it's not part of the agenda, but we can discuss it. It's good to think about what are the necessary sufficient conditions for a vector field in Rn to be conservative in this sense, to have this potential. Okay, so these are important vector fields, but beside this mathematical curiosity, I didn't tell you why they are important from physics point of view, right? So what is the physics importance of having potentials? That's the Can you guess what is the physical consequences of or importance of having a potential? So first of all, let's look at the equations, Newton's equations in this case, right? Newton's equations in this case tells me that q dot, equal to negative gradient of u. That's the equation. So what is the importance of, again, of this? Why this is important in physics?
So the external field and you setting it equal.
Yeah, there is a quantity that's conserved, and that has to do with conservation of energy, right? So there's a lemma here. This is conservation of energy. For the conservative fields. Basically, let F equal to 1 less gradient of U be conservative. Then the total energy E, by definition, which is equal to m over 2 q dot squared plus u of q. So this is the kinetic energy, and the next part is potential energy. Potential, I don't know. We just write u, the potential energy. Kinetic plus potential is conserved along motion. So what does it say? It just says that if you follow a particle that satisfies Newton's equations, is moving, because we know that there are a lot of solutions. Through each point and each velocity, there is a solution. So we have a lot of passes. Along each pass, the energy is conserved. So you compute the energy. How do you compute? It's very easy. So you have to add potential energy, kinetic energy, which is m squared. This is like v, velocity squared. Like this is the square of it, plus potential at that point. This quantity is constant. It doesn't change with time. This is conservation of energy, one of the most fundamental principles of nature. It's an amazing principle, is conservation of energy. So how to prove this? The proof is very easy. We want to show, because this depends on time, right? You follow this E along a path, right? We want to show that its time derivative is 0, right? So I just want to take d dt of E equal to 0 and show that this is equal to 0. That's what we have to do, right? So what is d dt of energy? Variation of energy along the path. Well, I mean, okay, so d dt of E is equal to, so we just go here. The derivative of that guy is m squared, m over 2 times 2. This is q double dot times q dot, right? Because this is a function of time. We are on a path, right? This is q double dot times q dot by using what's it called?
It's changed.
By using product rule. Yeah. So we need 2 here. Yeah. Okay. And I put 2 here. Okay. So this cancels with that. And then this guy is derivative of this guy with respect to time is gradient of u times q dot, the dot product with q dot, plus gradient of u dot q dot. Right? This is chain rule now, because u of q of t is u prime of qt times q prime of t, but this is the vector version. So I'm just writing. Is notation clear? Okay. But now we are not considering this E over a general curve, right? We are over a curve that satisfies Newton's equations. This one. So, or this one. So M Q double dot and this one is equal to negative gradient of U. So that's negative. I mean, here I should put dot. Negative gradient of U dot Q dot plus gradient of U dot Q dot. So this is the principle of conservation of energy. A couple of things to notice here. Now you see why physicists and also mathematicians, when they are doing physics, they insist of writing conservative field as F equal to negative gradient of U, not equal to gradient of U. I mean, mathematically, it wouldn't matter if you just change U to minus U would be. But if I define conservative force to be a force such that F is equal to gradient of U, then I should have said, for the principle of conservation of energy, that total energy is kinetic minus potential energy. And that's not very convenient. Like the total energy is the difference between 2 energies. So that's one thing. And also, you know now why we have 1/2 Q dot squared for the kinetic energy, and mass here appears. Exactly, this cancels, and otherwise you have to have twice kinetic energy or 1/2 of kinetic minus that would be crazy. But now we just say kinetic plus potential is total energy, and that's conserved. But this is conserved only for conservative fields. That's why they're called conservative, because we're conserving the energy along the motion. Any questions?
So I can see why if you have a conservative field and you can write it like that, then this follows. But the converse, though.
The converse.
Only conservative field.
I did not claim that.
Oh, okay.
No, I'm not claiming that. It just says that then total energy is conserved.
What is the case in the converse then?
If your field is not conservative, energy is not conserved, typically.
Typically. Okay.
Yeah, I think you can write down almost any example you write down. I think you see that it would. For example, one simple example is when you have dependence on Q dot, on friction, then the energy there is not conserved. You lose energy constantly. Okay. Because when you're moving on a surface, pushing, you know, a car on a surface that has friction, like usual car, any car with surface of the asphalt has friction, you lose energy. You have to spend energy, but after some point, you consume all your energy in your body, and you cannot push the car anymore. But not if there was no friction. If the car was just on a frictionless body, you could even, you don't have to keep moving. You just give one jolt, and then the car would go on forever. Does it?
Yeah.
Yeah, by the way, you should notice that kinetic energy and potential energy by themselves, they are not constant, they change. And there is a kind of give and take between the two, in the sense that as this increases, this potential has to decrease, and vice versa. There's a kind of fine tuning between the two. In the simplest example of this, of course, you can see a pendulum that's at this point, the velocity is zero because it has to come back, right? So the kinetic energy is absolutely zero, but the potential energy is maximum because it's yeah. In this case, the potential energy is the maximum. But when you come back here, potential energy is I mean, here the kinetic energy is maximum because it's just crossing this line, the vertical line, at maximum speed. We know that, and then it decreases, and kinetic decreases, potential increases. Okay. So, yeah, one thing that that we have to notice is conservation of energy tells us something interesting about motion in conservative problems. It just says that particles move in a hypersurface. So let me tell you what I mean. If you think of energy, right? So in a conservative system, so energy E, of course, is a function from Rn, cross Rn to R, right? I mean, this E is m squared, m over 2q dot squared plus u of q. So this is one factor Rn, this q dot is another factor from Rn, right? So this is a function on this space of 2n dimensions, and so the conservation of energy says that the motion is on level surfaces of these things, right? So these are like E constant. E constant. Because this defines level surfaces. And they are in constant energy hypersurfaces. So these are hypersurfaces. Right? I mean, how do you determine which surface your particle is? All you have to do, you have to find the initial position and velocity or momentum of particle. Then it gives you the value of the energy, and then you know which surface. You stay on that surface. The particle always stays on that surface. Okay, you can move. I mean, this has like E equal to constant. So dimension of this is typically 2n minus 1. but it can be less. There can be singularities on this thing, but generically it's a submanifold of dimension 2n minus. But this is important for some discussions. Okay. That's all I want to tell you about Newtonian mechanics, but we don't want to work within Newtonian context. We want to now move to a more elaborate context, which is Lagrangian mechanics. And that's what Lagrange and others did. So this is Lagrangian mechanics. So this is a famous principle of least action. So this is, I put action, I put the least in quotation marks because it's not necessarily least. It could be maximum, but in general is stationary action. Let me put it this way, it's stationary action. I tell you what we mean by stationary action. So it's a totally different foundation for mechanics. It's amazing that this existed. I mean, this is somehow quite remarkable. So so let me. So now in this case, so the starting point there's this thing called Lagrangian. L goes from Rn cross R to R. And typically we just write it again as L of Q, Q dot, and T. I mean, this Q dot is independent variable. Okay. So Lagrangian is just any function, smooth function, for example, of this thing. But in practice, in many examples, this L is really kinetic minus potential energy. This is minus. E.g., L equal to K minus U, which is m/2 Q dot squared minus U of Q. So kinetic energy minus potential energy. This is the Lagrangian. That's the first element of the thing. And there is also a concept of action. There is this action. The action is S of Q for a path, I'll tell you. This is equal to integral, for example, from T1 to T2, L of Q, Q dot, L of Q, Q dot, and T, Et. So here Q goes from interval T1, T2 to Rn. So we just take a path that starts at time T1 and at time T2 reaches the endpoint. So to this path, we give the associated number called the action of this path. So this is S, the action. So what is the now how equations of motions or dynamics, how do we know which passes are taken or favored by nature, which passes are not favored? Also, I write this principle now, and then we'll discuss the things. So this is called least action principle. Again, with this caveat that least really doesn't mean least, means stationary action principle. It should be called, but it's convenient to say least action. Okay, basically, particles move along paths such that this S is stationary. The motion of the system and only if delta of S equal to 0. Again, I mean, this is like physics notation. You have seen this in also random matrix theory literature in many places. Delta of S equal to 0. What does this mean? You're supposed to think of it as the derivative of a function of functional equal to 0. That's really what it means. So this is like you should think of it as derivative of some complicated function, which is this one is equal to 0. F prime of x equal to 0. This is comparable to that. And of course, this condition, f prime of x equal to 0, is a condition that you learn in calculus. For a smooth function, C1 function, a point, if it is maximum, minimum, extremum, or stationary, if and only if the derivative of the function at that point is equal to 0. So now I have to define what it means for this. What does this mean? What does this mean? Because our function here is not a simple function on numerical space. It's a function on a space of curves, right? S is a function on a space of all these curves. But you don't have to be very fancy to understand this at all. I mean, this is just a very simple thing. So in other words, you're just saying the following. So the meaning of this is the following. I.e., for any curve, epsilon from T1, T2 to Rn, such that epsilon T1 is equal to epsilon T2 is equal to 0, ds of little s, I put of s of q plus s little s epsilon at s equal to 0 is equal to 0. So first of all, you agree with me that this is now a normal, it's just a function of one variable s. This is a very simple object now, because I have fixed this perturbation epsilon, I have fixed this curve q, which I want to be solutions, and now it becomes just, this quantity just becomes a function of epsilon, right? And I'm saying its derivative at s equal to 0 has to be equal to 0. Let's see, unpack that equation a little further. What does that mean? Well, this is the curve, right? This is Q. And we are looking at some perturbation. This is Q plus S epsilon. You see, I chose epsilon in such a way that it's at two ends is 0. So when I add, so I still have the same endpoints in the space. Right? Still. Okay, so now what does this mean? This just means that the variation of this. So then this thing, when you change S, you get different variations and you come closer and closer. It just means that the variation of this quantity action along this direction epsilon should be equal to 0 for all directions epsilon. So basically, this quantity is the directional derivative of this function S, like from calculus, multivariable calculus. This is the directional derivative. If you want, the space of all maps is an infinite dimensional manifold, and its tangent space at this point Q is a space of all curves that vanish at these two endpoints. I mean, this definition is it's really taken from multivariable calculus. That's all that. Yeah, are you okay with it? Or any questions? So one question is, why this principle? Where this principle came from? I mean, this is absolutely strange. I mean, I should say, you could say Newton's law was sort of observations that Galileo, Kepler, and a lot of other people made. Still is an amazing law, but this is quite at a different level. I mean, you're just well, this has a long history. So basically, in a way, it goes back to Fermat, if you want. So this is related to or followed from Fermat principle of least time. So there was a big question in the early 17th century, and that's the question of refraction of light. So the question is, if light comes into this medium, like this is air or vacuum, and this is water. So experiment shows that actually it's the exit angle is a little less than the entrance angle. So the light is bent, so to speak, when it enters into this thicker medium, water. And the question is, what is the relation between this entrance angle, theta 1, and the exit angle, theta 2? And of course, there is a law, you know, this is experimentally arrived by a guy called Snell's law. You remember Snell's law?
There's like specific coefficients for each, and they take like their ratio or something for each.
It has to do with sine of this angle with respect to this. I mean, divided by the sine of theta 1 over sine of theta 2. I believe this is equal to n1 over n2. So n1 and n2 are refraction indices of light in this medium compared to that. I mean, in medium 1 and medium 2. So this is medium 1, this is medium 2. So people wanted to derive this from first principles. How can you prove this? And there was a precedent to this. There was a case which was done already 2,000 years before Snell. That is the law of reflection. A, B. For the reflection, we know that it reflects, so see here, for example, it reflects in such a way that the incidence angle is equal to exit angle. Right? Theta 1. This is much older than this. It's called law of reflection. But already Greeks knew, for example, this Greek geometer, physicist, was it Heron? Heron, yeah. I think it was Heron. Observe that this path is the shortest path among all paths connecting A to B. I mean, light could have taken something else, like this one, or this one. But this, exactly when theta 1 is equal to theta 2, is the shortest path. So this is the principle of shortest path. This was already done before Christ, I think, maybe around that time in Alexandria. I think Heron was a mathematician, physicist, scientist in Alexandria around 2000 years ago. Okay, so they knew that. And so it was natural to guess that, okay, in this case also, if you want to go from A to B, perhaps this is going to be the shortest path. And then you try to do this. But it turned out that this is not true, actually. What is at stake is shortest time, not shortest path. And this was quite a revelation. I mean, the reason that this is here also you can say is shortest time, because here the speed of light here and there are same. It's because in the same medium, so it doesn't change. So shortest time is equal to shortest path. But here not. Speed of light here, so it changes. If the speed of light is slower, it takes more time even to reach to. So Fermat invented calculus, actually, this condition of prime of x equal to 0. And then he applied this to this problem. So you just take this as a function of this x. And Fermat said that I know this point x is a point where the time at x, its derivative should be equal to 0. This is called Fermat's principle in optics, principle of shortest time. But I mean, of course, Fermat didn't have our notation, and this was a very, very complicated task. I mean, I have seen Fermat's paper, actually, I've looked at it. It's not a paper, it's a letter he wrote to another guy. At the beginning, he ridicules, I think, Descartes, because Descartes had claimed that he could drive Snell's law, and indeed he did, but from some wrong principles. I don't know how. Maybe Descartes was lucky because he made 2 mistakes and they canceled each other and he got it. First of all, he makes fun of Descartes. He didn't like Descartes. But then he derives it from right principle. So again, like so Fermat invented differential calculus, and this condition of extremum maximum minimum principle, derivative of the function should be equal to 0 at max and mean, it's definitely due to Fermat. Okay. So now the question is, how do you go from here to there? Well, it took about 100, 150 years. There was huge debate in 17th century, in 18th century, at the time of Euler and Maupertuis. Maybe I write this guy, Maupertuis. Euler, Bernoulli, etc. All these guys discussed this. So it looks like that. So because 18th century was the time of enlightenment, right? And people didn't want to believe that there is some divine philosophy or intervention behind motion of planets, stars, and everything. I mean, it looks like that there is some superior power that makes life in such a way that this quantity is maximum or minimized always. So nature does things in the most economic way. It's okay, but the question is, forgetting about those philosophical or religious discussions, what is that quantity you want to maximize or minimize? This was not known. It took a long time for that. Leibniz also entered this discussion, by the way. So it's a beautiful part of history of mathematics and physics, that discussions that they had. And then eventually, I think Euler and maybe Maupertuis, I'm not sure, they got it, but Lagrange got the full scale of things. Lagrange, he came across this quantity, and he said definitely that this quantity that has to be maximized or minimized is action, and action is kinetic energy minus potential energy. So what we're going to do next is we're going to use this, first of all, to show that this implies Newton's equations as a special case. But then we'll see that it's actually far more general than Newton's equations. So that's much more general. So I think I have to stop here because I have a Zoom call at 3, so I will stop. But would be good if you ask questions.
But T prime x equals 0.
Yes. That's the x that gives you the path, because the path really depends on this parameter x.
So I'm imagining you've got flat surface of water here, say in the air, you fire a beam of light at a particular angle you already know. Okay, you can get x from that based on where you fire it, and then that tells you the output angle.
Yeah.
Okay.
Yeah, I mean, basically, yeah, I mean, so this can go in any, you can send lights in any direction.
Right, but you're picking the initial angle, correct, or not?
No, not the initial angle. So you can formulate the question in different ways. I mean, for example, you can, which actually related to this, you can formulate it as, so from A to B, we can fix A and B, and then we can say among all possible broken paths that connect A to B, which one is the path that actually is taken by light. That's one way of thinking about it, which is more in line with this Lagrange's principle of, because here we are just so that.
But like, let's say I'm like sitting above the water with like a laser pointer or whatever. I could adjust the angle.
Yes,
fire
definitely.
So it feels like that initial angle should be also an input parameter as well, not just.
Okay, if you think of initial angle, then what B is out of your control.
Okay, so yeah, you pick A and B.
That's right. You can exactly. I mean, this is like a second order ODE. Right. You can either fix solutions by fixing the. It's a question of boundary value problems. Either the values at two ends, or position and velocity at the beginning, or other kind of boundary conditions you can put. Yeah. Exactly. That's a good question.
Can you write a Lagrangian down for reflection or refraction principles?
Yes, you bet.
Is it like
it's a very simple thing. It's just time.
It's just time.
Yeah.
Oh.
I mean,
yeah.
T is very, yeah. I mean, all you have to know is the relation. Yeah. All you have to know is the relation between n and the speed of light. So basically, the thing is B1 over C is equal to 1 over N1.
Okay.
This is the thing. This is the definition, if you want, of refraction index. 1 over refraction index is equal to speed of light in that medium divided by speed of light in vacuum. So you can see that the refraction index is always bigger than or equal to 1, and it's equal to 1 just for vacuum.
Right.
But always bigger than or equal to 1. So, yeah.
Okay.
So now then you can write this in terms of velocities, ratios of velocities.
Right.
And that's what it comes into the formula for. But in that case, the integration is done, and it's very simple formula. You don't need to deal with this very general principle.
Okay.
Yeah.
Well, next time we'll do some examples then.
Yes, we have to do some examples, absolutely. Okay, so we have to pause and